So today we are going to continue the mole concept, and we are going to learn something more important in terms of chemical calculations or stoichiometric calculations. I want to begin up with a knowledge of concentration of a solution. Concentration of a solution. So when we talk about a solution, we all know that solution is basically a mixture of a solute and a solvent. So how concentrated or how diluted that solution is basically inferred or calculated in terms of grams per liter or moles per liter. For instance, let's compare this. I'm having a solution that comprises of 100 grams of sugar in 1 liter or per cubic decimeters of water. This is solution 1. The other solution is 200 grams of sugar in 1 liter of or 1 cubic decimeter of solution. So by comparing solution 1 with solution 2, it says 100 grams in 1 liter, it says 200 grams in 1 liter. You can easily infer that this contains more solute as compared to 1. That means 2 is more concentrated and 1 is diluted. Take for instance some other example. It says I'm having a solution that comprises of 5 moles of sodium chloride per 100 ml of water. Or in the other part, I'm having, let's say, 1 mole of sodium chloride in 100 ml of water. So I can easily infer this is far more concentrated as compared to this. This becomes a diluted solution. So what we need to understand clearly is knowledge of concentration is very important when we are talking about stoichiometric calculations. So in chemistry, we would be discussing two different techniques or two different formulas to calculate the solution. We already know that moles can be calculated by grams of any substance divided by its relative atomic, molecular, or formula mass. So concentration can also be calculated in terms of grams, such as I mentioned, grams per liter. So I can generate a formula. It would be something like this. That means concentration of a solution can be calculated as grams of solute divided by volume of a solution in liters or cubic decimeters. It's the same thing. This is one concept or one formula. The other can be basically concentration of a solution can also be expressed in terms of moles of a solute divided by volume of solution in liters. So concept 2 is also known as molarity. We can usually use this term. Molarity is defined as the amount of solute in terms of moles dissolved in per liters of a solution. So how would we use this? Consider, for instance, this question. The question says a solution contains 5 grams of HCl, hydrochloric acid, in 1 liter solvent. So calculate the concentration. The question might be like this: calculate the concentration in moles per liter. So concentration in moles per liter is required. So how can I work this? It's easy. Since I'm given with 5 grams, so that is mass 5 grams, and I'm required concentration in moles. So first let us work out number of moles. So number of moles as given by the formula can be calculated as grams over relative molecular mass of the compound. HCl would be 36.5, and the answer comes out to be 0.14 moles per liter. So this is 0.14 moles per liter. This is one way of expressing a solution in concentration, or this is one way to calculate concentration. Take for instance this example. Calculate the number of moles of, question might ask us, calculate the number of moles of ferrous sulfate FeSO4 in 100 cubic centimeters of 0.1 mole per liter solution. So how can I proceed here? It's relatively a bit longer. It says I need to work out the number of moles of ferrous sulfate in 100 cubic centimeters of, this is given, 0.1 mole per liter solution. So the idea is I'm given with 0.1 mole per liter, and I'm required with to calculate the number of moles. Okay, so if I proceed in this way to work out the number of moles, I can simply study the relationship. It says 100 cubic centimeters and it says 0.1 mole per liter, and I'm interested in calculating number of moles. So what I recommend is that you just need to focus on the given numbers with their units. So you're given with 100 cubic centimeters and you're given with 0.1 mole per liter of any solution, and you are intended to work out the number of moles. So first is, this is a unit mismatch. It is cubic centimeters and it is cubic decimeters. So I would recommend that it should be, in order to proceed, you need to match these up. Either you convert this cubic decimeters to cubic centimeters, or you convert this cubic centimeters to cubic decimeters. So the formula is 1 cubic decimeter equals 10 to the power 3 cubic centimeters. It's normally known as 1 liter contains 1000 milliliters. So if I'm converting from milliliters to liters, I need to divide the term by 1000. So 100 cubic centimeters divided by 1000 would be 0.1, that is 100 over 1000. Now this was cubic centimeters and I divided this by 1000 to convert the answer into liters or cubic decimeters. So now I am having my volume in liters. So how would I work out moles? Moles can be calculated as 0.1, that is this volume here given, times 0.1 mole per liter. So 0.1 times 0.1 is 0.01 moles. So in continuation of our series of chemical calculations, we are here with some past paper examples. Question says now molybdenum. These all the questions have been selected from 2019 paper and it was variant 1. Okay, so molybdenum steel is made by reducing a mixture of molybdenum oxide with iron oxide and aluminium. So equations are given. This is molybdenum oxide and molybdenum. Okay, molybdenum steel contains 20.0% by mass of molybdenum. Okay, that means entire mass of molybdenum rounds up to 20% when we are considering molybdenum steel. Okay, calculate the mass of molybdenum oxide needed to make 1000 grams of molybdenum steel. So first thing that needs to be kept in mind here is we are given with mass of 1000 grams and this is of molybdenum steel. And according to the condition given in the question, only 20% of mass would be required to make the steel. So that means we first work out the 20% of 1000. So 1000 times 20%, that means 20 over 100. What do we have? We have 200 grams. That means what question is now asking us is we need to calculate the mass of molybdenum oxide by 200 grams, that is 20% of molybdenum. So according to the condition given in the question or the equation, since this represents a balanced chemical equation, we can easily relate molybdenum oxide with molybdenum. And to move further, I can start up with 1 mole of molybdenum is produced by 1 mole of molybdenum oxide. So in order to convert this moles to mass, I can write either 1 mole and 1 mole each for molybdenum and molybdenum oxide. Had this been 2 here, I can write 2 moles of molybdenum. Had it been 3 here, as you can see, this is 2. So I can write 2 moles of aluminium are being reacting with 1 mole of molybdenum oxide. Since aluminium is not to be catered in the given question, so we can start up with molybdenum and molybdenum oxide. So it says 1 mole molybdenum gives 1 mole of molybdenum oxide. This side represents molybdenum, the other side represents the other component, that is molybdenum oxide. So in order to convert moles to mass, what do? We multiply moles with the atomic or relative molecular or formula mass. So it is given in the question that the atomic mass of molybdenum is 96. So 1 times 96. Now this moles gets converted to grams of molybdenum is produced by basically. Now I need to work out the mass, relative molecular mass of molybdenum oxide. So mass of molybdenum, atomic mass is 96 times 1. Since there is only one atom, I can write 96. Oxygen 3. So from periodic table, the mass is given 16 times 3, 48. And then we have 144. Okay, so 1 times 144 grams of molybdenum oxide is produced by 96 grams. So in order to make this 96, 200, since it is given in the question that 200 grams of molybdenum should be used to work out and to find out the mass of molybdenum oxide required. So we can use stoichiometric calculations, or we can use the basic ratio technique or by proportion method. Since 96 grams is producing 144 grams, so 1 gram would give me 144 divided by 96 grams, and then multiplying this side with 200. So 200 times 1 is 200 grams. Here also 200 times 144 over 96 grams of molybdenum oxide. So by solving this side becomes 200 grams and this becomes 300 grams of molybdenum oxide. So what's important here is the answer is not 300. Why is that? So it says give the answer to 3 significant figures, and I'm having my answer as only 2 significant figures. So I can convert this 300 to 3.00 exponent 2 grams. So now this term has 3 significant figures. So I can repeat this calculation. I started up with from the equation 1 mole of molybdenum produces 1 mole of molybdenum oxide. Then we converted moles to mass using the formula we have done previously, mass over relative atomic formula mass or molecular mass. So we utilize this to convert from moles to mass, and then this becomes 96 grams and 144 grams. So according to the equation, this was not 96, this was 200. So in order to make this 200, I started up with making it initially 1. So I divided both the sides of the equations, left hand side and right hand side, with 96. I get 96 over 96, that is 1. So it becomes 144 over 96. Then I multiplied both the sides of the equation by 200. So this is my technique. You may use ratio method, you may use any method, whatever you like to get this answer. And this basically is the mass of molybdenum oxide. Then the other part of the question is related to empirical formula and molecular formula. So this question basically covers the entire aspect of empirical and molecular formula. We can proceed with a 6.30 gram sample of U. There is some compound U named contain 1.68 grams of carbon and 0.14 grams of hydrogen. Okay, and then furthermore it says my compound U contains besides carbon and hydrogen oxygen too. Calculate the empirical formula. So the approach that we are going to use is would be basically related to certain steps. So what I would recommend is uh, step one is you calculate the masses of all the components that are present in the question or in the compound. So you can clearly see that the mass of carbon and hydrogen is given. Mass of carbon is 1.68 grams and mass of hydrogen is 0.14 grams. But oxygen, there is no knowledge about the mass of oxygen. So what do we do? Basically what we can do is, since we know the total mass of the compound that was 6.30 grams, we can subtract the total mass from the mass of carbon, that is 1.68 plus 0.14. So we have mass of oxygen as 4.48. This is now 0.14 and this is 1.68. So step 1 would always be focused on calculating the masses. So once we know the mass, we can proceed to step 2 and step 3 relatively easier in a quicker way. So we have to divide these masses with the atomic masses. So 0.14 divided by 4.48 divided by 16. See, carbon has the atomic mass of 12, hydrogen has the atomic mass of 1, oxygen has the atomic mass of 16. This is the step 2. Whatever you have, whatever masses you have, you divide them by the relative atomic or atomic masses of the elements. So 1.68 mass grams was the mass given of was the mass of carbon that was given, and I divided 1.68 with 12. 0.14 grams was the mass of hydrogen that was given in the question, and I divided it by 1. 4.48 was calculated by keeping this knowledge that my compound is having a sample of 6.30 grams. Out of this 6.30 grams, I am having 1.68 as carbon and 0.14 as hydrogen. So what I did, I added these two up and subtracted from 6.30 and I obtained my answer, that is 4.48. That represents the mass of oxygen, and then after calculating the mass of oxygen, my step 1 ended and I need to divide that by atomic mass, that is 16. So this gives me 0.14 here, 0.14 here, and around 0.28 here. This term leads to our step 3. In step 3, we need to calculate the basically simple ratio. This represents the mole ratio, and I need to work out the simple ratio. How would I calculate the simple ratio? I need to focus on these values and I need to select the least of the values in between these three given. So 0.14, 0.14, they are basically the lower values here. So I need to divide them by all the values by the least value, 0.14. In step 3, you divide the answer of step 2 by the least answer you obtain in step 2. So we are obviously going to get 1 here, and 2 here. So empirical formula is can be calculated as CHO, since my compound was containing carbon, hydrogen and oxygen. So I'm using the relative symbols of the elements, and now this carbon is 1. So we don't usually write 1, but I can show you writing here 1, hydrogen 1 and O2. So it can be simplified as CHO2. This represents the empirical formula of my given compound. So by using the knowledge given here or explained here, you can always calculate the empirical formula or molecular formula of any compound. This is the most easiest technique to remember these steps, and you can get your answer relatively easier. Okay, so now moving towards the other part, it says a 0.086 grams sample of U is completely neutralized by 12.7 cubic centimeters of 0.150 moles per cubic decimeters potassium hydroxide. Okay, they're talking about neutralization reaction. 1 mole of U reacts with 2 moles of potassium hydroxide. Okay, then this knowledge is given that for every 2 moles of potassium hydroxide, I'm having 1 mole of U. Calculate the relative formula mass of U. So I need to work out the relative formula mass. So how would I proceed? I first need to work out the number of moles of U. So this needs to be kept in mind. I need to work out moles of U. So how would I proceed? See, first I need to calculate. This is my main objective. To obtain this, I need to calculate the number of moles of potassium hydroxide. So for potassium hydroxide, the relevant data says it is 12.7 cubic centimeters in volume and it have a concentration of or molarity of 0.150 moles per liter. So first I can convert this cubic centimeters to cubic decimeters and I divide this with 1000. So I can have my answer as 0.0127. This would be cubic decimeters. Then I multiply 0.150 with 0.0127. So I'm having my answer as 0.001905, or you can simply write this as 1.905 exponent minus 1, 2 and 3. This is minus 3. So this is basically the number of moles of potassium hydroxide. So according to the question, it says for every 2 moles I am having 1 mole. So I can create an equation here. For 2 moles of potassium hydroxide, we have 1 mole of U. That means for 1 mole of potassium hydroxide, we would have 0.5 moles of U. So if I'm having 1.905 into 10 to the power minus 3 moles of potassium hydroxide, then I should be having 1.905 into 10 to the power minus 3 times 0.5 U. So this gives me the number of moles of U. And what's the answer here? It is 0.0009525, or it can be simplified to 9.525 exponent minus 1 minus 2 minus 3 minus 4. So this basically represents the number of moles. So how would I proceed with the relative formula mass? It's now quite easier. I know have used the formula previously. Number of moles is equals to it was so we can proceed with number of moles is equals to mass upon relative formula mass. So I now need know the number of moles of U, and the mass of U was already given in the question, and I can work out the relative formula mass. How? See, this represents what? This represents number of moles of U, and the mass that is given in the question is 0.086. So using these two terms, I can calculate the relative formula mass. That would be around 0.086 divided by 9.525 exponent minus 4, and the answer is 90.288. So I can approximate that to 3. So this is 90.3. Relative formula mass is a unit of atomic mass unit, or U. Okay. Then it says, or you can simply write, don't get confused, AMU. Okay. Then what is the molecular formula of U? How would I calculate the molecular formula of U? So in order to calculate the molecular formula of U, you need to calculate a factor, that is a multiplier factor, and that multiplier factor is calculated as relative molecular mass, or mass obtained from the molecular formula, divided by the mass obtained from the empirical formula, that is empirical mass. So I just calculated the empirical formula in the previous part, that was CHO2, and I'm having now my molecular mass or relative formula mass. So molecular mass is 90.3, and this is here, and empirical mass can be calculated from the empirical formula. This would be carbon 12, hydrogen 1, oxygen 16, but there are 2 atoms of oxygen, so 32. So we can have 5 and 4. So this is 45. So factor would be around 2 point something, so I get 2 as a whole number. So CHO2 was my empirical formula, as you can see here. Time it by this multiplier factor 2 in a subscript, so it becomes C2H2O4. So this 2 times 1 2, 2 times 1 2, 2 times 2 is 4. So basically this gives us the molecular formula, that is C2H2NO4.